Okay. All right. So any questions to get us started today? Okay. So what I'm going to do is I'm going to continue talking about our Lewis structures. As I said, that's the primary goal of this chapter, is to work on Lewis structures. So what I'm going to talk about to begin with today is a phenomenon that's observed with molecules, with many molecules, and it's called resonance. And resonance has to do with what's called delocalization of electrons. Okay, so remember, electrons are waves, right? So even though we have all these different symbols for the electrons, so sometimes we use this symbol, right, to indicate that it's a particle that's charged. Sometimes we use a dot to represent the electron, right? So again, you're sort of thinking of it as a particle there. What we also know is that the electron is a wave. And this leads to a complicating issue when it comes to Lewis structures. Because when we talk about Lewis structures, we're representing the electron as pairs, right? A pair of electrons that are, quote, localized, meaning they're in a specific location, right? So for example, if we write the Lewis structure for water, really what we're claiming is that you have a pair of electrons that are localized as a lone pair on the oxygen. Okay, so that lone pair is not interacting at all with the hydrogen atoms according to the Lewis structure. Same with this pair over here. It's localized on oxygen. Whereas this pair right here, that's a bonding pair, right? That bonding pair is still localized. It's localized between the oxygen and hydrogen atoms. So what we're going to claim now is that there are certain molecules and ions. So often when we're doing Lewis structures, we'll use the two words interchangeably. Even if something is an ion, we'll call it a molecule, even though it's really charged. We're going to talk about structures where the electrons are not localized on one or two atoms, but are delocalized across three or even more atoms. So we call this delocalization. So this is the case where electrons are spread out, if you want to use that terminology, across three or more atoms. And we refer to this phenomenon as resonance. Okay. So again, the electron is a wave. So imagine that you've got three carbon atoms in some sort of arrangement. It is possible for the electron under some circumstances as a wave to spread out across all three atoms, right? So that's an electron wave. But we generally don't consider the electron a wave when we do Lewis structures. We generally consider them as little dots, as particles, or a line, which is two particles that are stuck together as a bond, right? But in fact, they are waves, so they are capable of spreading out across three or even more atoms. So how do we recognize this phenomenon? Because what I'm going to claim is that in the case of water, it appears as though these electrons are, that it's pretty accurate. They really are on that oxygen atom. And this pair of electrons here, even though they're waves, are pretty much localized on the oxygen atom. There's good evidence for that. Likewise, there's pretty good evidence that these two electrons here are localized between the oxygen and the hydrogen and not really interacting with this other hydrogen on the other side. So they really are localized. But in some cases, electrons are not localized. So let's take a look at how we can recognize when that happens. Often, oxides exhibit this behavior. Again, I'm going to use two different words. Oops, I'm going to try to spell them correctly, though. Delocalization or resonance. For the most part, we can use those two words interchangeably. So oxides, what do I mean by that? You'll see it in molecules like SO2, SO3, N2O, SO2 minus 2. I'm sorry, SO3 minus 2. SO3 minus SO4 minus 2. Okay. PO4 minus 3. NO2 minus, NO3 minus. So notice what all of those have in common. They're all oxides. They all are a non-metal, sulfur, nitrogen, phosphorus, with a bunch of oxygens, 2 or 3 or 4. There's some other ones as well. ClO2 minus, ClO3 minus, ClO4 minus. Again, these are all oxides. They're all a central atom that's a non-metal with some number of surrounding oxygen atoms. And sometimes they're charged and sometimes they're not. I can give you even another one. Here's another one, CO3 minus 2. There's one with carbon, right? So there are many of these types of species where you observe resonance. So if you're looking at whether you want to analyze, oh, do I think that this might have resonance, might have delocalization? Take a look at the formula, and if you see that there's a non-metal with surrounding oxygen atoms, there's a good chance you've got resonance there. Those are not the only examples where it happens. There's many others, but this is one big class of substances where you see resonance, which we would say oxides, okay? So let me show you how we go about this. I'm going to pick SO2 as the first example because it's uncharged, it's neutral, so we don't have to add any extra electrons due to the charge. It only has 2 surrounding oxygen atoms, so it's relatively simple. So I'm just trying to pick one that's simple. So SO2, what we would do is we would put the sulfur at the center and then assume 1 bond to each surrounding oxygen, right? So we're going sort of stepwise how we do Lewis structures in general. So then we look for the positions of the atoms in the periodic table. And what we find is that sulfur is in group 6A. So that means it has 6 valence electrons. And oxygen is also in group 6A, above sulfur. So it also has 6 valence electrons. So that means we have 6, 6, and 6. That's 18 electrons, right? So we have 18. So 18 valence electrons. Not bad. We got 18 valence electrons. So now we've already used 2 bonds. And remember, a bond is not 1 electron. A bond is 2 electrons. So that's a total of 4 electrons. So we subtract that 4. That means we have 14 more electrons to allocate around those 3 atoms. And as I said before, you have options in terms of how you distribute these, but in general, you want to distribute them as pairs, and it's not a bad idea to distribute them around the surrounding atoms first, stopping at 8. Remember, stopping so that the surrounding atoms have no more than 8. So I put 6 around each oxygen, and now each oxygen has 8, right? But that's 12 that I just used. So I still So what I'm going to do is I'm going to take the last 2 and put them on the sulfur. Okay, so that's all 14. So now we're at 0. Okay. Good. Oh, oops. Okay, that's good. All right, so now what I'm going to do is I'm going to notice that the sulfur in the center doesn't have 8 electrons. Okay. So what I'm going to do is I'm going to take 1 pair of electrons from the oxygen on the left and push them until they form a bond. So now we have 2 lone pairs on the oxygen on the left and a double bond to the central, then 3 lone pairs over here. Okay, so that looks like, oops, sorry, forgot that pair of dots there. So that looks like now the sulfur has 8. Remember, what you do is you get the surrounding atoms up to 8, and then if the central atom doesn't have 8, you push a pair, a lone pair. Sometimes you have to do 2, right? But at least 1 lone pair to get that central atom up to 8. The pair that you move over is now counted by both atoms in terms of the octet rule. Okay, so the sulfur now has 8, and the oxygen still has 8. And that looks like a valid Lewis structure. We've got our octet rule taken care of for all the atoms there. Okay. All right, let me come over here. Okay, so the next step is to say, well, the reason that we pushed that pair of electrons from the atom on the left was that we wanted the sulfur to have 8, and it only had 6. But I picked the oxygen on the left. I could have picked the oxygen on the right. So why did I pick the one on the left? Well, I just happened to see that the oxygen on the left had 3 lone pairs, so I picked it. But the oxygen on the right also has 3 lone pairs. So I could have picked that one as well. So what I could have done is I could have said, no, it's not this one that's occurring. It's this one over here. It's that pair that's getting pushed over. And if I had done that, then the double bond would be to the oxygen on the right. And you'd still have a single bond to the oxygen on the left with 3 lone pairs. Okay, so let me actually, I'm going to draw this right back over here. So this is what I'm going to call this structure 1, and I'm going to call this one structure 2. So this is structure 1 and this is structure 2. That's what you get out of pushing those electrons. And what I'm going to claim is that not only are either of these Lewis structures valid, because they, again, you got the octet rule. It's not like we broke any rules of drawing Lewis structures. Both are fine. What I'm going to claim is that the electrons will do both, meaning the electrons will move to form structure 1 and they'll move to form structure 2. And then those 2 structures will combine. And what you'll get is an average of those 2 structures. So in reality, meaning as far as we know, both structures are valid. And the actual molecule is an average of both. That's what resonance is. Resonance is average. It's an average of more than one Lewis structure. So when someone says, hey, this molecule exhibits resonance or delocalization, what they mean is it's going to actually be an average of the two Lewis structures that we do. Now, even up to today, because Lewis structures have been around a long time now, long meaning around 70, 80 years, 80, 90 years actually. So even though they've been around a while, there's still really no good way that people have developed to sort of indicate resonance in a real accurate way when you draw the Lewis structure. So there's two different typical ways. One is to say, hey, here's Lewis structure 1, here's Lewis structure 2. It's an average of those two. So you just explicitly write out both structures and then indicate that it's an average of those two. The second way is with sort of a hybrid logic or hybrid notation. What you do is you say, well, what's the difference between those two structures? The difference is one of them has a double bond on the left and a single bond on the right. The other one has a single on the left and a double on the right. So how do we indicate that it's an average of both of them? Well, we say, well, what's the average of a single bond and a double bond? Right? So how do we do averages? Well, the way you do an average is you say, hey, you have one number, let's say it's a 1, and you have another number, let's say it's a 2. The average of 1 and 2 would be, what you do is you'd add them and then divide by how many you have, right? So like if I count 1 marble in one container and 2 marbles in another container, the average would be 1 plus 2 divided by 2. So you get 1.5. So we do the same thing with the bonds. What we do is we say, well, what's the average of a double, which is 2, and a single, which is a 1? Well, it's 1.5. So we write it this way. 1.5 is written as a line plus a dashed line. And so that's a way of showing 1.5 bonds. And then the same thing on the right side. You have a single and you have a double. Well, the average of 1 and 2 is 1.5. So you write it as a line and a dashed line. So now you got 1.5 bonds. And keep in mind, those are averages. And typically when you do this, you don't even draw, if you're going to use this notation, you don't even draw the lone pairs because that's just too complicated. Because in one case, you have 3 lone pairs, and in another case, you only have 2. So how do you draw, 2.5 lone pairs? So we're going to try to avoid the dots altogether. So there's 2 ways to deal with this. One is just to explicitly draw out the 2 forms as different structures, and then just indicate, hey, it's really an average of these 2 structures. The other one is to take the average of the number of bonds. So if you have a double and a single, that's 1.5, and to write 1.5 as a line plus a dashed line, and that would be 1.5. So a chemist would instantly recognize, oh yeah, you have a line and a dashed line. That means you've got more than 1 bond, but less than 2, right? And they would also recognize instantly, oh yeah, you've got 1 Lewis structure here. Here's another. The only difference is where the bonds are and where the lone pairs. So that's definitely resonance. Okay. So mainly what you're trying to do is you're trying to communicate to people through this analysis how many bonds these atoms have. Okay. When molecules have resonance, when they exhibit resonance, it actually gives them a more rich chemical personality. So for example, water, because it does not exhibit resonance, that limits its chemical reactivity, what it can do. But when molecules exhibit resonance, that makes them open up to certain types of reactions. So organic chemists in particular are very interested in resonance because if they can figure out that a molecule exhibits a resonance, that allows them to sort of set up certain types of reactions so that they can make new types of molecules and form new types of bonds based on them exhibiting resonance. That's one of the things you deal with if you take organic chemistry is observing, oh yeah, that molecule is going to have resonance. So now that means we might be able to do this type of reaction. Okay, we're not going to get into that in this course. Here, all we're really trying to do is to predict whether a molecule or an ion is going to have resonance. And if we can predict that, we want to say, well, what are those different resonance forms going to look like? What are these two different structures going to look like? Okay, so let me show you another example here. I'm going to show you one that does not have oxygen. As I said, most of them have oxygen, but I'm going to show you one that does not. Okay, this is an interesting one. This is called azide. And I believe it has resonance. Sometimes I forget, but I think this one does have resonance. So let's take a look. Now, this is an interesting molecule because it has 3 of the same atom. I guess you would call this a triatomic ion. A triatomic ion. There are a few triatomic ions out there. There's this one, which is called azide. There's another one called ozone, O3. And those are the only 2 that I know of. So let's take a look at how we do this. You got 3 nitrogen atoms. And really all we're doing is we're just trying to see, hey, octet rule. We're just going to draw as many Lewis structures as we can in which each atom has 8 electrons. Okay? And so if, it means that you're going to have a triple bond on this side or a double bond on this side, as long as the octet rule is met, it's a valid Lewis structure. And then you just try to see how many you can draw. So with this one, we might be able to draw a few. So let's see. Keep in mind, it's negative, right? That means you're going to add an electron. You add an extra electron. Okay, so when it's negative, that doesn't mean you lose an electron. It's actually, if it's positive, you lose an electron because the electron's negatively charged. So if it were -2, we would add 2 electrons. So nitrogen is in group 5A. That means it has 5 valence electrons. There's 3 of them. And then you got that extra electrons, so you got 16. Again, many structures have even numbers of electrons because even number means that you're going to have a spin up and a spin down in some orbital in the molecule or the ion. So even numbers are more favored with molecules in nature. Odd numbers of electrons they're sort of odd. They're uncommon. They exist, but they tend to be very reactive. We call them radicals. An example of that is nitric oxide. NO has 9 electrons, 9 valence electrons, and that makes it very reactive. And actually, humans actually use NO in nerve transduction because of its reactivity. Okay, so we got the number of electrons. We've already used 4, right? Each bond has 2. We're assuming at least a single bond. So that's 4. So we're down to 12. Okay. So again, what I would recommend is just getting the surrounding atoms up to 8 by putting 6 on. Right? It's multiples of 8 is what we want, the octet rule. So now each of those surrounding atoms have 8. But this is not a valid Lewis structure. A valid Lewis structure, with a few exceptions, is 8 electrons around each atom, except for hydrogen, right? Hydrogen's only 2. That's the duet rule. So we've accomplished it with the 2 surrounding atoms, but we need to do the central atom as well. So what do? We need to get it up to 8. So one way, so I'm going to try to use my space efficiently and effectively here. So what I'm going to do is I'm going to say, wait a minute, here's one way in which this could happen. Let's consider equal, right? If I take one pair and push that over, okay, what happens? Now the nitrogen in the center gets another 2, so it's up to 6. So maybe what I'll do is I'll push 2 pairs over, and now that central atom will have a total of 8, right? It had 4, it's getting another 4, so that's 8. And again, when something becomes a bond, both atoms get to count it. So the atom on the left still gets to count those electrons. So that would deal with it perfectly. That would take care of it right there. Oh, by the way, the whole thing's negative. So we got that annoyance of the extra step of having to put the brackets in, right? If it's an ion, you got to put the brackets in there for those structures. So we're going to have a triple bond over here. So it's going to be triple bond with one lone pair remaining. The central atom doesn't have any lone pairs. And then the atom on the right has 3 lone pairs. Okay.
Sir, why we cannot have double bonds on both sides?
Ah, very good. You're seeing it. You're seeing the pattern. This is puzzle. What we're doing is we're doing puzzle.
Okay.
That's a second solution. That's a valid solution. So what I'm going to do is, I guess what I'll do is I'm going to, write this again, because I want you to be able to see exactly what I'm doing. And sometimes when I erase stuff, you lose track of what I'm doing. So I'm going to go back to the starting point where that central atom doesn't have 8 electrons. And I'm going to do exactly that. I'm going to take one lone pair from each surrounding atom. And that will do the same thing that the first structure did, right? It's going to get that central atom up to 8. Again, the goal here, the power of this analysis is the octet rule, really. It comes down to that. The idea that you're just trying to get every atom up to 8 with the exception of hydrogen. And so when we do that, we get a new structure. And now it's a double bond to the left and a double bond to the right. And then we're going to have 2 lone pairs on each of the surrounding atoms. By the way, a little bit about this arrow notation. You don't really need it for this course, but if you are going to go on to take organic chemistry, the arrow notation, which we call electron pushing, is used throughout organic chemistry. It's a way of communicating what's happening in the molecule. So sometimes what people will do is if you're pushing one electron, you use a half arrow, meaning that the head of the arrow just has one side, right? See what I did there? And then if you're doing 2 electrons, you start the arrow in between them, and then you show a head that has 2 sides to it. So if you're trying to communicate that you're pushing 2 electrons, you use this type of arrow. And if you're just pushing one of the electrons, you do this. And you put the arrow, the tail of the arrow right above that one electron. Again, we're not going to get into that details in this course, but when you take organic chemistry, you'll see that that's the notation that people typically used. This is still sort of evolving in organic chemistry. People are still trying to learn how to teach and communicate organic chemistry to people because it's still, modern organic chemistry is still a relatively young science. It's been around for, around 100 years or so. And that's still, historically that's young. Newtonian physics has been around for 400 years, okay, or 350. Okay, so there's a second structure. So I'm going to call this one structure 1. They're both valid. They're both valid structures. And we could make arguments about maybe one's a little better than the other, but evidence suggests that the actual structure of this azide ion is some average of more than one structure. So both of these are probably valid to some extent. But there's still one more possibility, right? And the other possibility is, I'm going to write this over here. Okay, so there's 2. So again, I'm going to start with our starting point, just so that you have it all on the same piece of paper. And the starting point was you had 3 lone pairs on the surrounding atoms and no lone pairs on the central, but the central only has 4 electrons. So now what I'm going to do is I'm going to say, hey, the first one was 2 lone pairs on the left. Why not 2 lone pairs on the right? Why not do that? And that's perfectly valid too. So what you get when you do that is a triple bond on the right. And then you get a negative charge here. So there's number 3. So take a look at what you have. You got 3 different structures. All of them have the same arrangement of atoms. So the atoms, we haven't changed the atoms anyway. All we've changed is where the electrons are, where they are. But again, all 3 fulfill the octet rule for each atom, right? Each atom's got to have 8 electrons. And so each of them have 8 electrons around each atom. Of course, we don't have to worry about hydrogen here. And so they're all valid. So one way of communicating this would be to put it into words. We would say, hey, it looks like there are 3 valid Lewis structures. 3 valid, meaning octet rule, Lewis structures. So we believe that this particular ion exhibits resonance. Okay, so if someone said, hey, what about the azide ion? Does it exhibit resonance? You would say yes. It appears as though there are 3 valid Lewis structures, so this particular ion exhibits resonance. If we wanted to communicate something about the structure of that, what we could do is we could just show all 3, or we could do some averages and just indicate how many structures are involved. So what would be the averages? Well, it's interesting mathematically how it works. You got 3 structures. So this bond is a triple, right? So that's 3 bonds. This one's a double, so it's got 2 bonds. And this one's a single, right? So I'm comparing the same atoms, the relationship between the atoms. So what's the average of 1, 2, and 3? Well, 1 plus 2 plus 3 is 6, but you got 3 different structures, so 6 over 3 is 2. So it actually, the average is a double bond. But you have to be careful. We're not saying that there's only 1 structure and it's a double bond. We're saying that there's 3 structures and the average is a double bond. And then same thing on the right side. You got a single, a double, and a triple. There's 3 structures. So if you add them up, 6 bonds divided by 3 structures, you get a double again. Again, that's your average, an average of double bonds. And if you're trying to communicate it that way, you don't write in the lone pairs. You just show the number of bonds that are in there. But we're going to point out it's an average of 3 different structures so that people understand we're not just saying, hey, it's 1 structure with double bonds. It's an average of a bunch of these. So if you were to take organic chemistry, after a while of doing this over and over and over with different structures, you would very quickly recognize, oh yeah, there's resonance there, and you would indicate that, or there's not resonance there, and you wouldn't indicate it. At this stage, what we would do is we would be pretty explicit with you. We'd say, hey, here's a structure. Do you think it has resonance, right? So we're going to kind of prompt your thinking about resonance. We're not going to give you a structure and just say, draw the Lewis structure, and then, oh, tricked you. It turns out it has resonance, and you only drew 1 of the structures. We'll prompt you about resonance here, okay? So let me show you another one. I'm going to show you one. Should I do? Yeah, let's do ozone. Ozone is such a common example of resonance. Ozone is a very special form of oxygen. Okay, so if you have atomic oxygen, just O, it's extremely reactive. It's unstable, we would say. It will very quickly react with anything that it can find. You know, it will just, anything it collides with, it'll react with. It could be it could be a metal atom if it finds a metal atom. If it finds a nitrogen molecule to react with that, it reacts with everything. So you don't see very much oxygen, atomic oxygen in nature, at least in our atmosphere on the surface of the Earth. You might see it in outer space because there's nothing to react with. The form of oxygen that we're familiar with is O2, right? And it's historically it's been a little confusing. And you may remember back in chapter 3 when we were talking, you know, hey, write the combustion reaction and then you got to write O2, not O, right? It's one of those diatomic elements. So this is, it's diatomic oxygen or molecular oxygen. The British call it dioxygen, which I like. I try to use that word because that way it's very explicit. Dioxygen, so O2. I like that. Okay. I think Alex does a little bit of that too. So ozone is also so this one's reactive too. O2 is reactive. For those of you that are biology majors, you may have learned that, in the early days of life on the Earth, going back billions of years ago, photosynthesis probably didn't exist. Photosynthesis came about later. And there were species that were alive on the Earth, microorganisms that, had been around for a long time, hundreds of millions of years or even billion years. And then certain species learned how to do photosynthesis. They evolved to do photosynthesis, and that produced molecular oxygen. That's a byproduct of photosynthesis. And that oxygen is very reactive, and it just essentially killed off the vast majority of species on the Earth. So there was a massive extinction event that occurred over some period of time. And those early species, they now only exist in, at the bottom of the ocean, in the crust of the Earth, away from the oxygen, right? I guess one exception to that would be botulism, right? Botulism exists on the surface of the Earth, but only under certain circumstances. But yeah, the huge die-off, because oxygen is so reactive. It's not as reactive as O, but it's pretty reactive. It reacts with almost all the elements in the periodic table. Well, there's this other one called ozone, and this one's even more reactive than O3, than O2, maybe less reactive than O. And so one way to form O3 is you just take this very reactive O and react it with this pretty reactive O2, and then you get this O3. It's also reactive. So they're all oxygen is very reactive. That's why the Earth's crust is mostly oxides, silicon dioxide, sand, right? Or glass, very stable. Oxygen reacts with stuff like crazy. So there's O3. This is O3, it's ozone. And ozone, it turns out, is very important. What happens is in the upper atmosphere, oxygen reacts with O2 to form ozone. And this one absorbs ultraviolet radiation in the atmosphere. And the sun produces an enormous amount of ultraviolet radiation. And that ultraviolet radiation is very powerful, very highly energetic, and can damage, it can kill cells, it can destroy life, actually. And so what happens is that ozone up in the upper atmosphere just absorbs ultraviolet radiation like crazy. And that protects the surface of the Earth from getting so much UV. Even though it's absorbing a lot of UV and other molecules are absorbing UV, if you go out in the summer and the sun is shining and you go out without any clothes on, you can get cancer over time, right? So it's pretty dangerous radiation. Ozone's very protective. So let's take a look at drawing Lewis structures. So ozone is 3 oxygen atoms. It would be kind of cool if it formed a little ring like a triangle, but it turns out it doesn't. It just forms a straight chain, okay? There is one molecule that exists with 3 atoms in a ring, and it has 2 hydrogens coming off like this. But generally, when there's 3 atoms, it's very hard to form a ring. So ozone is not a ring, and azide is not a ring. It'd be exciting if it were. But this is called cyclopropane. It's very reactive, though. It's unstable because that ring. It's just those atoms don't want to be confined to such a small location. So it's actually used as an explosive. You can explode things because it's so reactive. So ozone is a straight line. Its oxygen is in group 6A. So that means it has 6 valence electrons, but there's 3 of them. So you got 18 electrons. We've already used 4. So you're down to 14. Okay, so it has a couple more electrons than azide does because oxygen is a little bit further to the right on the table. So what do? As I said before, you take some of them and distribute them around the surrounding atoms until they're up to 8. So I just did that. So now those 2 oxygens are up to 8. But that's 12 that I just used. So I got 2 left. So I'm going to put them on the central atom. So now the oxygen in the center is pretty close to 8. It's got 6. It's getting there, right? But again, non-octet. We want octet. So here's what I'm going to do. The first thing I'm going to do, I'll do it over here to the left, is I'm going to pick one surrounding atom. They're the same, so I can pick either one. I'll pick the one on the left. And I'm going to push this pair of electrons over. By the way, in terms of these Lewis structures, you could have picked the lone pair at the top or the bottom or the one on the left, even if you want, but that would be sort of awkward to do on the left. You'd have to draw this big arrow all the way around. So generally people, just for convenience, will pick the pair that's closest to the central atom. So that would have been either the top or the bottom one, doesn't matter. And so what do you get? You get a double bond, right? And that double bond will result in the central atom having 8 electrons. This one doesn't have any charges. Ozone is a neutral molecule. So we don't have to draw the bracket notation for this one. So there's one structure right there. That's perfect. Octet rule for every atom, we're set. But again, looking for patterns, I could have picked the other oxygen on the right, a pair of electrons from over there. So what I'm going to do is I'm going to push one of these pairs instead. So just to indicate this is structure 1 and this is structure 2. Now what we get is the double bond on the right. Okay. So it looks like there's 2 structures here that are possible. I don't think there's 3. Could there be 3? Well, the way we got 3 structures with the azide was somewhere in there was a triple bond, right? So we got 2 of them because of a triple bond, but there's no real good way to do a triple bond, because what happens is if you do a triple bond, so for example, suppose I said, hey, I'm going to push another pair over to give a triple bond. That now gives this oxygen 10 electrons. That's no good. We want 8. So you say, oh, okay, well, I have a solution to that. I'll push this pair over there. So now this oxygen, even though it gained 2 over here, it lost 2 there, so it's back to 8. Well, again, the problem is now this oxygen on the left has 10, right? If you push another pair over, it gets 10. So it doesn't look like there's a 3rd structure. It looks like there's only 2. And so what we would do is we would communicate that, in fact, it looks like there's 2 valid Lewis structures. And this molecule exhibits resonance. By the way, you can only get resonance with 3 or more atoms. You can't get resonance with 2 atoms because wherever you put the electrons, they're on those 2 atoms. So it's got to be 3 or more. Then what we could do is we could say, in structure 1, there's the possibility of a double or a single. The average of a double and a single is 1.5. So I could write 1 and a dash, right? So that's 1.5 bonds. And then on the other side, one of the structures had a single and the other structure had a double. Again, that's 1.5 is the average. And you say, hey, these are averages of 2 structures, 2 Lewis structures. And then you'd be set, right? So there you go. So usually oxygen. So if you have a central atom that's a nonmetal with a bunch of oxygens around it, 2 or 3 or 4 oxygens, that's when you see resonance. But there are a few others where you have like O3 or N3 minus. If you have 3 atoms and it's charged, I mean 3 elements and it's charged. So for example, SCN minus, that exhibits resonance. N3- 3 atoms in a charge, that exhibits resonance. There's a few others out there, but generally, if you're going to do resonance in a general chemistry course, we're not going to have you do the most complicated molecules. It's usually you want to notice it non-metal with surrounding oxygens, and then 3 atoms with a charge. That's generally the types of problems you'll see where there's resonance. Okay. Any questions? Okay. So the next topic I want to talk about then is exceptions to the octet rule. Now, what happens in chemistry is typically you learn a topic, you learn the theory behind the topic, and you apply the theory and it works. And then what we do is we give you exceptions where it doesn't work. So this is no exception to that. There are cases where the central atom appears to be stable with not 8 electrons. So what I'm going to claim here is that the octet rule can be violated sometimes. So mainly what you want to do at this stage is you want to be able to identify when is that going to happen. So I'm going to give you the sort of lowdown on when that happens. It's relatively rare, but the examples where it does happen are important molecules. They're used throughout the chemical industry, so we have to be aware of them. So the first one is boron. And that's element B. It's number 5 in the periodic table. So let me, I've got, I think, just enough time here. So let me do this. I just want to sort of show you in terms of the periodic table where these elements are that I'm talking about. Okay, so those are your main group elements, the main group like alkali metals, alkaline earth metals, and hydrogen. Now, in a sense, hydrogen violates the octet rule, right? It's got its own rule. It's the only element that has its own rule. It's called the duet rule, right? So that's a violation right there. So moving over, again, we're going to ignore the transition metals because they're not useful for Lewis structures. And then there's 2 elements here that I'm going to kind of box off, boron and aluminum. And then next to them, carbon, silicon, nitrogen, phosphorus, oxygen, sulfur, selenium, arsenic. Wow, I'm already out of fluorine. Fluorine, chlorine, bromine, and iodine. And then you can also do neon, argon. So neon, argon, krypton, and xenon. Okay, so I'm going to draw boxes around the exceptions to the octet. Okay, so it looks like a lot, right? By the way, helium's up here. But it's really not a lot, and it's not a lot. I'll show you why. So I'm going to write here boron and aluminum. So that's these 2 over here, which is Al. Sometimes they have 6 electrons. Okay, so that's an exception. Sometimes they only have 6. So let me show you what I mean by that. BH3. There's no way to draw the Lewis structure here where boron has 8. It can only have 6. And let me show you why. Boron is element number 5, but it's actually in column 3A. So that means it has 3 valence electrons, 2p1, I'm sorry, 2s2, 2p1. So boron has 3 electrons. Each hydrogen has 1, so that's a total of 6 electrons, right? So the Lewis structure for borane is this. There's just no way to get 8 electrons in there. So this is 6 electrons. So those 2 elements will exhibit this phenomenon where they have 6. And it does make them reactive. I'm not going to go through the chemistry of it, but it turns out by having 6, that makes them reactive because they don't have 8. So there's way for them to react with other elements. But you would just remember that for these 2 elements, if you have 3 surrounding atoms, it's going to have 6 valence electrons. So that's a violation of the octet rule. Okay. So boron and aluminum, they will have 6 electrons. What are the requirements? The requirement is that the boron has to be at the central atom. Okay, so the boron is the central atom, and it's bonded to 3 different atoms. If it's only bonded to 3 atoms and it's the central atom, it's going to have 6. And the same goes for aluminum. If aluminum is the central atom, the surrounding atom, all bets are off, then octet rule is going to fulfill. But it could be 6 if it's just not. If it only has 3 atoms bonded to it. Okay, so there's your first one. That's these 2 here. The rest of the ones that I have boxed off here, the phosphorus, arsenic, sulfur, selenium, chlorine, bromine, iodine, krypton, and xenon, all of them kind of follow a similar pattern, which is they're going to have more than 8 electrons. But again, okay, so let me list them. PAS, SSE. So all these ones over here on the right, the first requirement for breaking the octet rule is they have to be the central atom. Okay, so if they're not the central atom, just use the octet rule. But if they are the central atom, they could have more than 8. And again, if they have more than 8, that's violating the octet rule. Okay. So here's how it tends to work. The first example, the first class category, is where you have more than 4 surrounding atoms. So if you have more than 4 surrounding atoms, you can't have 8 electrons around the central atom. Because remember, even a single bond is 2 electrons. So if you have more than 4 atoms surrounding the central atom, you have more than 4 bonds. So if you look at a chemical formula and you see, okay, here's our central atom, and there's more than 4 surrounding atoms, you know right there it's a violation of the octet rule. Okay? In that case, what tends to happen is a single bond to all of them. Just draw a single bond in, and that tends to be what happens. So if you do that, this phosphorus is going to have 10 electrons, right? Each bond is 2. So look at the formula. If you're concerned about a violation of the octet rule, it's got to be one of these elements here. That element has to be the central atom, and there's more than 4 surrounding atoms. So the same thing goes with the sulfur. If it's got, oops, I'm sorry, just give me 1 second here. If it's got more than 4 surrounding atoms, it's going to be a violation of the octet rule. Okay, let me see if this now works here. There we go. Okay, so in that case, the sulfur would have 12 valence electrons, right? Because each bond is a single bond. By the way, I haven't drawn in the lone pairs on the fluorines or the chlorines there, just to sort of save a little time. But what we're trying to evaluate here is whether the central atom is going to have more than 8 electrons. So this would be called an exception to the octet rule. There's names to it. It's sometimes called the expanded octet. But again, what you're going to be looking for are these elements on the right side of the periodic table, these nonmetals that are starting in the third row. Notice none of them are in the second row. So we don't see violations in the second row like this, but if it's the third row or beyond, and you see more than 4 surrounding atoms, you can have a violation, okay? Now, there's a third category. So we did 2. We did the boron and aluminum. If boron or aluminum has 3 surrounding atoms, then it's going to have 6, and that's a violation. If the central atom is on the right side of the periodic table and there's more than 4 surrounding atoms, then that's going to be a violation of octet. The third category, again, are these oxides. These oxides are interesting. So what you see sometimes is, again, let me draw these elements just so you can sort of see where they are relative to each other. Okay, I think those are all the ones we need to, I put arsenic in there too, right? So the ones I was talking about are these. These are the elements. Again, they start in the third row, not in the second. If you have them as a central atom and they have oxygen on them. So there's an example right there, right? PO4 3-, that's an oxide. BRO3-, there's an oxide. So the central atom is one of those elements, and it's surrounded by a bunch of oxygens. Here's another example. By the way, I put krypton and xenon here. These are included too, I'm sorry. So xenon, there's an example right there. So there, notice the pattern here. They're the central atom, and you got a bunch of oxygens surrounding them. Then again, you're probably going to have expanded octet. So you'll observe it there. So let me show you an example of this. Just about out of time, so I'm going to do this very quickly. Phosphorus is in group 5, 5a, so it has 5 electrons. Oxygen is in group 6, so it has 6, but there's 4 of them, so that's 6 times 4 is 24. And then you got 3 extra electrons here. That's a lot of electrons, 32 electrons. We've already used 8, so we're down to 24. So I'm going to do exactly what I've done before, which is get the surrounding atoms up to 8. And then put the charges out here, right? So that looks like an octet rule for everything. Now what I'm going to claim is what you do is you take the central atom, and again, it has to be one of these elements here, one of those, what is that, 3, 6, 9 elements, surrounded by oxygen atoms, okay? And you draw in double bonds by pushing pairs of electrons. Okay, so then you get, oops. There you go. And if it's in this column, you get 1 double bond. If it's in this column, you get 2 double bonds. So push 2 pairs if it's in that column. So if it were sulfur at the center, you would push in 2. Okay. Tomorrow, what I'll do is I'll talk more about these elements here. Okay, so we'll go over it a little bit more tomorrow and finish up this discussion. But for right now, what I would say is you know, boron and aluminum, 6. And then if it's more than 4 surrounding atoms, that's expanded octet. And then tomorrow I'll talk more about this idea of how you push these electrons over to get the expanded octet. Again, these are the exceptions, okay? The exceptions are discussed in section 8.7. So we're talking about 8.7, okay? And then we'll wrap up chapter 8 tomorrow. I will post this video up in the next hour or so. And any questions? Okay, so reach out to me if you have any questions, and good luck with everything this week. We're getting toward the end here. This is the last primary topic, is chapter 8. There is an extra credit assignment for chapter 9, which you can work on next week if you want to, but this is the last required chapter for this course. If you are going to go on to take organic chemistry, I would recommend that you do the extra credit for chapter 9. But again, it is extra credit. It's optional. You don't have to do it. But if you're going to take organic, I would recommend it because it could help you for that course. Okay. Take care, everybody.
Thank you.
Have a great day.
Bye. Thank you.
Bye-bye.